In this video, we are going to be studying how circular motion is related to simple harmonic motion. In this picture here, we have a turntable turning that has a ball on it, and there's light shining on the ball, and the shadow will show a sine curve. And the example we have here of that, we have this very similar example. And so we have an object moving up and down in simple harmonic motion. You see that this motion up and down matches the circular motion. What's interesting here is the circular motion is at a constant speed, but the linear motion is not at a constant speed. You'll see that this velocity, the velocity vector here, it's always changing. In the circle, it stays constant all the time. The displacement stays constant all the time. But if you look in the linear sense, the displacement's always changing, the velocity is always changing. And you'll notice that the largest velocity occurs in the middle, and zero velocity occurs at the ends. And the displacement is opposite of that. It has its largest displacement at the ends, and its minimum displacement in the middle, which is zero. Now if I throw the acceleration vector on, it actually has, it's similar to the displacement where its maximum is at the end point. So the acceleration is maximum at the ends, and zero in the middle. Acceleration is zero in the middle, maximum at the ends. In the circle, again, the acceleration is constant the whole time. So we're going to have some equations that we're going to use today that relate simple harmonic motion to circular motion. It allows us to solve some simple harmonic motion equations. Now we're going to look at some relationships that occur in simple harmonic motion, and we're going to just think of a mass moving up and down in a spring. We think of these relationships. And when a mass moves up and down a spring, and when it completes one full cycle, that's called the period T. Now, we have something that we have to keep clear. This omega in simple harmonic motion stands for angular frequency. In circular motion, it's angular velocity. Now, in circular motion, you'll see it written as delta theta over delta t. And so it says angular velocity equals change in angular displacement over time. In angular frequency, you'll see it more as angular frequency equals 2 pi all over the period. And omega, it's in radians per second. You have 2 pi radians. So this is the equation down here, omega equals 2 pi over t, that we'll be using more often. And there's another relationship that we have to know, that frequency is equal to, this is the cycles per second or oscillations per second. We were just discussing angular frequency, now we're discussing frequency. So it's often, instead of the period, it's more convenient to speak of frequency f of the motion. The frequency being just the number of cycles of the motion per second. For example, if an object on a spring completes 10 cycles in 1 second, the frequency is 10 cycles per second. The period t, or the time for one cycle, would be 0.1 seconds. Frequency and period are related this way. So you can then also say, well, since angular frequency is 2 pi over t, angular frequency is 2 pi f as well. So there's two types of frequencies that we have to deal with. Angular frequency, which is in radians per second, and then there's frequency, which is in cycles per second, oscillations per second, or you can call it hertz as well, vibrations per second, but typically it's called hertz. An equation for displacement is this, x equals a cosine theta, or theta can be written as omega times t. We saw in the previous problem that omega equals theta over t, so you just substitute in. And the maximum value that x can be is a. So we have here a top view of a ball on a turntable. The ball shadow on the film has a displacement x that depends on the angle theta through which the ball is moved on the reference circle. We're not going to use this equation. I just want you to realize that it's a cosine curve, but the biggest thing I want you to realize is that x has a maximum value of a. Cosine omega t runs between 1 and -1, which makes this between a and negative a. So the maximum value x can have is a. The velocity equation has sine in it. Now it has negative there because the derivative of cosine, or the slope of a cosine, is a negative sine curve. So we have velocity equals a omega sine omega t. Now, what's important to realize, though, in this problem is that V max is a omega. This is the equation that we are going to worry about. That the maximum velocity that this object on a spring, oscillating on a spring, has is equal to the amplitude times the angular frequency. Here's the velocity vectors shown. So this is the tangential velocity that we're talking about here. Velocity v of the ball's shadow is the x component of the tangential velocity of the ball on the reference circle. So this x component right here of this tangential velocity, that's the velocity. That's this v max equals a omega. That tangential velocity does not change. You'll notice that the circular motion piece, the velocity vector never changes, but the simple harmonic motion piece, that velocity vector is changing all the time. And you'll notice that it's the x component of this vector. It's always changing. The x, or actually in this case, it's the y component that we've set up here. It's the y component of this velocity vector. The velocity of the mass in simple harmonic motion. And it's just set up here so that it's the x component here. But anyway, the maximum velocity is a omega. It's always this value, a omega. So let's go ahead and try a problem. It says here, a diaphragm of a loudspeaker moves back and forth in simple harmonic motion to create sound. The frequency of the motion is 1 kilohertz, which means 1,000 hertz, and the amplitude is 0.2 millimeters. What is the maximum speed of the diaphragm? And then part B says, where in the motion does the maximum speed occur? So we'll go ahead and use our equation, V max equals a omega. I'm going to convert the omega to 2 pi f. And then plug in our values. We plug in our amplitude, which is 0.2 times 10 to the negative third meters per million grams. And then 1,000 hertz here times 2 pi. So we get an answer of 1.3 meters per second. And its maximum speed occurs midway between the two positions, or at x equals 0. Now we're going to look at the acceleration vector. It's similar to the velocity vector, except it's a omega squared cosine omega t instead of sine omega t. But really the most important part that we want to worry about is a max is a omega squared. So if we go ahead and take a look at this, it's again the x component of the centripetal acceleration that's here. And we'll go ahead and look at our circular motion. You'll notice this is our circular motion here, and our centripetal acceleration is always pointing towards the center. And you'll notice this y component of this acceleration vector is always this acceleration here. So the acceleration happens to be 0 in the middle, and it's the maximum value at the ends. So let's go ahead and try a problem here. It says the loudspeaker diagram in figure 10.12 is vibrating at a frequency of 1,000 hertz, and the amplitude of the motion is 0.2 millimeters. What is the maximum acceleration of the diaphragm, and where does this maximum acceleration occur? So we'll go ahead and just use the equation we just. In this problem here, we're going to, and so we plug in our equation. Acceleration equals a omega squared. For omega, we plug in 2 pi f. Plug in our values, and we end up with an acceleration of 7,888 meters per second squared. Now we're going to look at frequency of vibration. Whenever a spring is moving up and down, we can always say that the force acting on it from the spring is negative kx. Force also equals ma, so kx equals ma, substitute to each other. X equals a cosine omega t, so we can plug in that for this x here. Acceleration is negative a omega squared cosine omega t, plug that in right there. We end up with this here. And when we cancel out our cosines and rearrange our equation, solve for omega, we end up with another equation for angular frequency is square root of k over m. So here's our example problem. This device consists of a spring-mounted chair in which the astronaut sits. The chair is then started to oscillating in a simple harmonic motion. The period of the motion is measured electronically and is automatically converted into a value of the astronaut's mass. The spring used in one such device has a spring constant of 606 newtons per meter, and the mass of the chair is 12 kilograms. The measured oscillation period is 2.41 seconds. Find the mass of the astronaut. So pause the video and see if you can use what equations we have here to solve this problem. So we're going to go ahead and use omega equals 2 pi over t, which also equals square root of k over m. Plug in our values here, rearranging this. And actually the best thing to do is square both sides, because then you have 2 pi, or 2 pi has to be squared, so that's really 4 pi squared. All over t squared will equal k over m. Plug in your values and you'll end up with m equaling 89.2 kilograms. The mass of the astronaut, though, you have to subtract the 12 kilograms from the chair. So the astronaut is 77.2 kilograms, so you have a chair that's 12 kilograms. So in this video we learned some new formulas for simple harmonic motion. We looked at the motion of an object moving in simple harmonic motion and looked at what its velocity looked like, acceleration, and its displacement. Displacement's in red, velocity's in blue, acceleration in black. And we also looked at the graph that goes with that, the three graphs that they're all sine or cosine curves to go along with that as well. Reset this. Put this down. Let it go. So you'll see one starts as a cosine curve, one starts at negative cosine, one started as a sine curve.